So now let's do the experiment optical fiber. So we have to determine the numerical aperture and bending loss in the given optical fiber. Okay, so this is our apparatus. So we have here we have a helium ion laser, and here we have optical fiber. This is the mounting case of optical fiber, and here you can see this black wire. This is actually the optical fiber, and here if you see this, this is the internal input end of the optical fiber. You see it clearly. Yes, this one. So hello everyone. Today now we will do the experiment numerical aperture. So we have to determine the numerical aperture and bending loss in the given optical fiber. Okay, so here is our apparatus. This is the helium neon laser, and this is optical fiber, and this is a mounting case of our optical fiber, and this black wire is actually the optical fiber, and here as you can see the input end of the optical fiber. Yes, that's how. Okay, so we have to put it like this, and this is it is going to like here. First of all, we have to this experiment has two parts. Okay, so first we have to determine the numerical aperture, and in the second part we have to determine the bending loss. So here this wire is going to the external end of the optical fiber, and here it is placed a detector, and whose output is connected to the digital nanometer. As you can see, this is the digital nanometer. So let's turn on the circuit, turn on this apparatus. Okay, so first of all, let's understand that what we actually have to do in this experiment. Okay, so suppose that this is a external end of our optical fiber, and this is our detector. Okay, so this is also movable, and this is also movable. Okay, now what is numerical aperture? Numerical aperture is actually the accept this sign of this acceptance angle. Okay, so we have to measure this whole distance. Okay, so suppose that this is our optical fiber output, and this is our detector. Okay, so first of all what we have to do is that move our optical fiber towards us. Okay, so it will come in this position about here. Okay, and our detector will remain fixed in its original position. Okay, now we have to move it until the output that we get it minimizes. Okay, so first of all in this in this condition we have to maximize the output. Okay, so we have to output we have to maximize. Okay, so now as we move this output of optical fiber towards us, the output will decrease, and a point will come when it will saturate. So at that point we have to stop. So and we have to measure this reading of detector. Now this is a now we have to in this is done. Now we have to fix this output. Okay, now we'll move this our detector from here to here. So we'll move our detector from here. A point will come when our current will be maximum, then it will start decreasing. This is whole distance will be capital D. Okay, and midpoint will be somewhat here, and this angle will become the acceptance angle. Okay, so we'll just calculate, use the formula perpendicular up, and this is our base. This is our distance from small d is distance from detector to output of optical fiber. So we'll just use this formula. Okay, this is this formula, theta equals to tan inverse t by t. Okay, now let's quickly do the experiment. So this is our experiment. This is our let's uh, actually the power is off, so I'm just telling you quickly. So first of all we have to move, this is the output of optical fiber. First of all we have to move it using this screw. We have to move it towards us, okay, like this. As you can see, it is moving very slightly. And then we have to do this at two distances, okay. At one distance at small d equals to 5 mm, and other at small d equals to 10 mm.